In this video, we shall look at determinants. We shall see what a determinant is, and we will also show you how to calculate determinants. Important applications is to compute inverse of a matrix. So we use determinants to compute the inverse of matrices. We can also use the technique of evaluating determinants to calculate the so-called cross product of two vectors. So here is the definition of it. A determinant of a square matrix is a single number that is a function of the entries or the elements of that matrix. Of course, this number can be a positive number, could be a negative number, or it could be identically zero. So these determine the geometrical interpretation of that square matrix at hand. But we shall not go into these here. If you have a square matrix, say matrix A, its determinant can be written in following notation. So you can write the determinant of that square matrix like this, or you can denote the determinant of that A like that. So these are possible notations that we use to denote a determinant. Before we show you how to calculate a determinant, let's look at a couple of important theorems. Let's assume that you have a square matrix A, and its transpose is that. So the determinant of that square matrix A equals the determinant of that transpose of A. That is to say, the value of a determinant of a square matrix remains the same if rows and columns are interchanged. So that is Theorem 1. The second theorem is, let's assume that we have another square matrix, namely matrix B. Then the determinant of that product of A and B equals the determinant of that square matrix A times the determinant of that square matrix B. So this is the second theorem that we need to know here. It's important to note that matrix B and matrix A are square matrices of the same order. Let's begin with a 2 by 2 determinant. So right here you have two 2 by 2 square matrices, matrix A and matrix B. So how do we determine the determinant of matrix A? The determinant of matrix A is written in the following manner: 2 minus 1, 3, 2. So we don't use brackets, we use just two vertical lines. And it's straightforward to evaluate a 2 by 2 determinant. It is that element times that element minus this element times that element. Meaning in this case, 2 times 2 is 4, minus 3 times minus 1 is minus 3. So the answer is 7. Next, let's calculate the determinant of the transpose of matrix A. The transpose of that square matrix A is 2 minus 1, 3, 2. So we interchange the rows into columns. So the determinant of A transpose is written as 2, 3 minus 1, 2. So this times this, that is 4. Minus that times that, minus 3 is 7, which is theorem number 1 that we outlined a few minutes ago. Now let's look at matrix B. Determinant of that matrix B is written as 7, 2, minus 3, 4, enclosed in two vertical lines. So this times this is 28, minus this times that is minus 6, so you get 34. Now let's look at transpose of that matrix B. That is 7, 2, minus 3, 4. And you see that the determinant of that transpose of B is 7 minus 3, 2, 4. Meaning this times this is 28, minus that times that is minus 6, so you get the same 34 as for matrix B. Again, verifying theorem number 1. Now let's look at theorem number 2, which says the determinant of the product AB equals the determinant of matrix A times the determinant of matrix B. From our previous video, we can easily take the product of these two matrices, and the answer is a 2 by 2 matrix with elements 17, 0, 15, 14. So the determinant of this AB is quite simply that, and which we can evaluate by taking this number times that number minus that number times that number, which is 17 times 14 minus 15 times 0, and you get 238 for that. So let's check theorem number 2. Determinant of product of two square matrices of the same order equals determinant of that matrix A times determinant of matrix B. Now we know this is 238. Individually we know the determinants of the matrices A and B, so 7 times 34. This is indeed 238, which verifies theorem number 2. Now we will show you how to calculate a 3 by 3 determinant, namely determinant of a 3 by 3 square matrix such as the one shown here. Let's look at matrix C first. So the determinant of matrix C is written in the following manner: 2, 1, minus 1, 1, minus 2, 3, minus 2, 1, 2, enclosed between two vertical lines. Evaluation of a 3 by 3 determinant requires the knowledge of evaluating a 2 by 2 determinant, which now we already know. The technique is pretty simple. First, we need to identify the row or the column that we want to work with. It doesn't matter which. So let's work with the first row, that row. Step number 2 is to calculate the cofactors associated with all these three elements on the first row. Let's do just that. So let's determine the cofactor associated with that element 2 by crossing 2 in two mutually perpendicular directions. We are left with a 2 by 2 determinant. We know how to calculate this 2 by 2 determinant. So that is minus 4 minus 3. So that is minus 7. To this number, we have to multiply the so-called polarity of this number 2. The polarity of element 2 is dictated by the column and the row. So it inhabits row number 1 and column number 1. So the polarity of it is just 1. So the cofactor of number 2 is just minus 7. So the first term in the evaluation is that cofactor that we have just calculated times that element associated with that cofactor, namely 2. Now let's move on to the second element in the row, which is 1. We are left with a 2 by 2 matrix. Let's determine the determinant of that. That is 2 minus minus 6. So 2 minus minus 6. That is an 8. What is the parity of this number 1? It occupies row number 1, but column number 2. So its parity is minus 1 raised to the power 1 plus 2. So you get minus 8. So the second term in the expansion in evaluating the determinant of C is that minus 8 times that element, which is 1. Now let's do the last number in the first row, which is minus 1, like that. So you're left with a 2 by 2 matrix again. So this is 1 minus 4, which is minus 3. The parity of this minus 1 is minus 1. It occupies row number 1 and column number 3. So 1 plus 3. So that's going to give you a minus 3. So the last term in the expansion is that minus 3 times that element itself, which is minus 1. So the answer you get is minus 19. So that is the determinant of this matrix C. Now let's calculate the determinant of the transpose of C. So the elements of such a matrix is 2, 1, minus 1, 1, minus 2, 3, minus 2, 1, 2. So rows become columns. Now let's use the second row to determine the determinant of this transpose of C. Using the same way, this is crossed out. So you're left with these two elements. So this times 2 is 2. That times that is minus 6. So you get 8. The parity of 1, because it occupies row number 2 and column number 1, is 1 plus 2, so you get minus 8. So to get the first term in the expansion of the determinant, you have to multiply this cofactor with that element, which is 1. So the first term is simply minus 8. Now let's move on to the second element in the row, which is minus 2. So you have 2 times 2, that is 4, minus 1 times minus 2, which is 2. So you get 2. The parity of minus 2, since it occupies row number 2 and column number 2, is 2 plus 2, so you get 2 for the cofactor of that element minus 2. So the second term of the expansion is that 2 times that element minus 2, which is minus 4. Now let's do the last element, namely 1. So this times this is 6 minus 1, so that is 7. The parity of that, row number 2, column number 3, 2 plus 3, so you get minus 7. So minus 7 times that 1 is just minus 7. And you see, you get minus 19, just like for C. Confirming theorem number 1, which says determinant of a square matrix equals to the determinant of its own transpose. Now let's look at this matrix D. Now its determinant, of course, can be written in the following manner, like that. So let's work with the first row. So you're left with that. So 1 times 1 is 1 minus 3. So that is 4. The parity of that is minus 1, 1 plus 1. So you get 4 times that element 1. The first term in the expansion is quite simply 4. Now, term number 2. So this times that is minus 2 minus that 6. So you get minus 8. The parity is minus 1, 1 plus 2, so that's an 8. So 8 times with that element, which is minus 1, is the second term of the expansion. And finally, the last term, so this times that is 2, minus that is 2, that is 0, which means the third term is quite simply 0. So the determinant is minus 4. Determinant of matrix D is minus 4. Let's quickly test theorem number 2. Taking the product of C and D, we get the following matrix. We simply give the result for the product. 11 minus 6 minus 1, 0, 1, 1. Using the method that we have just described to determine this determinant of the product of C and D, that's going to give an answer of 76. Now let's see if we can get 76 by multiplying the determinant of D and C separately. Determinant of matrix C was minus 19, and for D, the determinant is minus 4. So the product of those two is minus 19 times minus 4, which is just 76, thus confirming theorem number 2. Thank you for watching.